Alrighty, folks, so good morning. Today we are moving along with our study of rocks. Last time we spoke, we just did a general overall introduction, and at the very end of that, almost the very end of that, we told you some rock symbols that you might see and so on and so forth. And we just sort of had a generic igneous rocks one. It was just the little asterisks, if you remember. And that maybe that got your hopes up that we wouldn't go into igneous rocks too deep. But sadly, maybe for you, that is not the case. We will certainly be talking about igneous rocks a lot. This first one here talks about how igneous rocks come together, how magma or lava comes together, and essentially ends up covering one type of igneous rocks, the intrusives, the ones that cool inside the earth. We talk a little bit about the other ones, extrusives as well, but extrusive igneous rocks are covered much more in depth, or along with, I should say, volcanoes, which is also hopefully obviously related to this topic. So we'll have 2 full lectures on that, and a fairly decent video on Mount St. Helens at some point as well. So without further ado, again we continue our discussion about rocks. You know how there's those memes out there? You could still see memes, right? There's those memes out there that say I was this days old or something like that, when I'm embarrassed to say way too recently.
Oh yeah, I was today years old when I found out something.
Yeah, that exactly. Way too recently for this one. I just never bothered to look it up for whatever reason. I don't know. I like etymology. We started, the semester talking about word origins and prefixes and suffixes and everything. But, yeah, igneous. All right, ignite, ignition, igneous rocks. So, means fire. Fire. No, it's not fire. What's that a picture of? Lava. Good. And what's another word for lava or magma? Sorry, that we should be able to, should know at this point, so to speak. What is it actually? What is lava or magma? Liquid rock. I like that. I would have used the word molten, but I like liquid much better. It is molten rock, all right? And even more basic than that, what is it? What is it made up of? Great guess, but why isn't it minerals yet?
I don't know, it's because they're too hot to come together.
Well, what's our definition? Somebody help her out here. Well, definition of a mineral. Everybody, you should know this at this point. Naturally occurring, inorganic, crystalline.
Oh wait, it's not crystalline.
It ain't crystals yet. It's elements. Okay? It's that molten elemental stew that we talked about way back when we were building the earth. And we said it was just this flaming ball of goo hanging in the sky, right? So it is not minerals, it's elements. And that's just exactly why we talk about this after the minerals chapter. Okay? Because, we told you all this stuff about being a mineral, and now we're actually going back to just a little bit before this stuff is minerals. And as we make igneous rocks, we're actually growing minerals along the way. It's pretty neat. So, igneous rocks are rocks made from mineral crystals that form or grow in cooling magma or lava. All right, and that happens either at the surface of the earth or inside the earth. It is possible to cool off and crystallize inside the earth. You just have to move a little bit away from the heat. So, which one is which? Again, many of you know this already. So this molten mineral mixture, this elemental goo or stew, it has lots of names that I call it. All right, when it's inside the earth, we call it magma. When it's at the surface of the earth, we call it lava. And for our purposes, they are the same stuff. Just one's at the surface, one's not. Because arguably it all starts subsurface, right? Now, you could argue, as I said, this is for our purposes, you could argue that there are certain chemistries of magma that are maybe more inclined to make it to the surface and so on and so forth. But like many of the things we'll be talking about, that is its own semester-long class. All right, igneous petrology, making igneous rocks. I did not enjoy it very much. Again, I was talking about this in lab yesterday, actually. We had a guy fresh out of one of those University of California places. It wasn't Berkeley, but one of them highfalutin. And he showed up at good old YSU, Youngstown State University, and talked about 1.5 feet over our heads the entire semester. We just kind of blinked at him. Had no clue what he was talking about. So, I learned a lot about magma and lava since then. But back in my formative years, not so much. Bad professorialism. No. He was a good guy. He just really didn't know what he was walking into. So, we don't worry about that. And there's that phone call I said I probably might be getting. It is not. This is even weirder. I don't know where I was with my long rambling thing there, but... huh?
You just got finished with the crappy.
Yeah, I know. I thought I was past that. But, Dr. Ray, yeah, good guy. But, at any rate, so, lava, magma, one's inside the earth, one's at the surface of the earth. Short story long, as they say. Come on. Does that have any effect? Of course it does. Thank you for asking. So, crystals that grow inside the earth grow much slower than crystals that grow at the surface of the earth. Grow and cool, we kind of use interchangeably, all right? So, they grow much slower, which means they have a longer time, a larger opportunity to get large. We call these coarse grained, all right? Coarse as in like black pepper is coarse grained, okay? Or coffee, if you grind your own coffee. So coarse in that sense. The proper word is phaneritic, okay? I don't use that word very often. This is our formal presentation, our formal PowerPoint. In lab, you're going to hear me say coarse grained over and over and over again. But the tables in the book, the tables in your lecture in your lab, will say phaneritic as well. And I definitely won't ever say plutonic rocks, okay? that is incredibly antiquated. But again, it still shows up in the textbooks. Pluto, god of the underworld, it's just a thing they make. At some point, you'll read about things called plutons, all right, which are large bodies of magma that cool eventually in the surface, underneath the surface of the Earth. So I never say plutonic. I will occasionally use the proper word phaneritic there. Picture like a head of lettuce or a head of cabbage growing in your garden. The longer you let it grow, the bigger it could get. All right. So that's that. On the other hand, oh no, we got pictures. So coarse grain, you can actually see the different grains in there. When you see different colors, that's different crystals, that's different minerals. The last one there, the gabbro, it's kind of hard to see, but in person you'll be able to make a little bit out. Don't worry about felsic intermediate mafic yet. That's coming. 3, very common, coarse-grained, igneous rocks. Phaneritic igneous rocks. Phanero means visible. All right. For some strange reason, you remember the geologic time zone scale. There's the biggest grouping over on the left is the Phanerozoic. Okay. Zo always means life. We've got a zo down the street. All right. Protozoa, zoology. You've heard zo lots of times. So Phanerozoic. Phanero means visible. All right. So visible life, in this case, visible crystals. All right, on the other hand, we've got our extrusive igneous rocks, as I started to say. These guys grow at the surface of the Earth, therefore they grow from lava, not magma. And they cool, by comparison, really, really, really quickly. All right, lava cools within days, if not within minutes or hours if it hits water. All right, lava that comes out at the ocean floor or at the coastline and hits water, that cools super duper. All right. Whereas you go back to the intrusives for a moment, I don't necessarily want to give you, times, but you're more on the thousands of years kind of thing. And you'd think for that much gap on that spectrum there that you'd see a bigger difference in crystal size, but it really isn't. It's like the point of your pencil to the eraser of your pencil. Now, there are some huge examples out there, okay? They're rare. But generally speaking, when you think about, again, those countertops that you've seen at various places, they don't have, foot-wide crystals in them. They're about the size of the eraser on your pencil, thereabouts. Whereas these guys are more like, again, your pencil point. Your pinhead would be stretching it a little bit, but, very small. You won't see the different colors, as you'll see in a moment. So we use the word aphanitic. Remember, a as a prefix means not. Phanero still means visible, so guess what? Not visible. And I do occasionally say volcanic rocks, but not a lot. Way more than I say plutonic at any rate. Yeah.
So where does obsidian fit in all of this, since that's volcanic grass?
You'll see. You'll see. One of the ones that cools really, really, really quick.
Ah, okay. So it would be exclusive in this sense.
It is, but they have their own when we get to lab. Obsidian and pumice and scoria, they all sort of have their own little subgenre in there.
Right.
But they are, definitely extrusive because they're volcanic. But yeah. Anybody else? Okay. So, despite the one in the middle there where you can see some colors, generally speaking, these guys go into what I'm going to call pastel-y, sort of a heathered blend of things, okay? We talk about this a lot in lab because one of your jobs in lab is to identify the minerals that are present. You need those to know what rock you're looking at, whether it's the felsic, the intermediate, or the mafic, which again, I don't want you to worry about just yet. We'll get there in a moment or two. All right. That's all based on mineral content, and we use your knowledge of minerals to say, oh, I recognize that. That's orthoclase feldspar. I saw that a couple weeks ago. So that must be one of the felsic rocks, blah, 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 blah. Well, when we get to the fine grain, you can't really see the crystals. Instead, you have to picture, that stereotypical little painter's palette. You always see the guy, the thumb goes through, and you've got your little daubs of paint there. All right. So you've got let's just say you've got some orthoclase, you've got some albite, which was the white stuff, right? You got a little bit of black stuff, and you got some clear sparkly paint. You got your glitter glue in there too. All right. So in your coarse-grained rock, you're going to see that pink, black, white, and glittery. In your extrusives, all right, it's just going to be, if you took a little dab of each of those, went over on the side of the palette and mixed them together, and then painted your rock. So what was a pink, black, white, and sparkly rock turns into a pinkish gray rock. You'll see in lab. Don't worry. Point is you can't see the crystals. But then there's these guys. And this is really why I'm trying to use the phaneritic and the aphanitic, because I have always used porphyritic. Really, because there's no other name for it. It is mixed grain, I guess we could say that. We've got coarse grain, fine grain, and now mixed grain. And what happens with these guys is that they start to grow inside the earth. You get some nice, big, pretty crystals forming. And then for whatever reason, topologically speaking, that stuff gets exited out to the surface. And all the goo around those big, pretty crystals grows very quickly. I call this, I always have my cute little colloquialisms or whatever you want to say. I call this chocolate chip cookie rock, because that's kind of what it looks like. You got the cookie, that fine-grained matrix. It's like the movie, that's what it was. The matrix is the background, right? So you've got that fine-grained matrix with these large crystals, and those large crystals are called, guess what? Porphyrs. That's why it's porphyritic. Contains porphyrs. We've got one. One of your specimens will be a porphyritic igneous rock. We'll never name it formally as such, but it does cause much consternation amongst you guys. And ta-da, there you go. Yeah, very burnt cookie, but yeah, you get the idea. Or more so, one of those cheaters my mom would used to make when she wouldn't even bother to make cookies, where they just kind of like spread out the dough in the pan and then cut it into squares, whole house bars, whatever they used to call them. But yeah. So those are your porphyrs. There's your fine grain matrix. There's a mixed grain rock. So, what we've been talking about are textures, okay? You could loosely think of it as how they feel. That's the way we usually use the word texture, okay? They don't necessarily mean that. They're talking about grain size or lack thereof. However, in your nimble fingers, uncalloused as they are at this young age, you might actually feel some differences. So we've talked about phaneritic or coarse grain, aphanitic or fine grain, porphyritic or mixed grain already. There's two textures left, vesicular and glassy. Vesicular is pretty easy. It means it has vesicles. Good? No, probably not good, because many of you might not know what a vesicle is. These are the rocks with pores or holes in them. The holy rocks, as we like to joke in lab. All right? They're full of holes. Give me an example of a rock that's full of holes. Igneous rock. Pumice, yeah. All right. And then scoria is the other one. Now, back when I first started, we used to say, oh, the gas grill rock or the landscaping rock for scoria. Well, they don't put stuff in gas grills anymore. It's all these heat dissipating shields and
Infrared.
well, I don't got one that fancy, but I do have these silly little metal shields that they do a good job of dispersing the heat, but I miss good old fashioned fake briquettes in there. So you've seen this stuff. If you've seen it in landscaping, it's usually red because it's prettier, I guess. It's that real rough, porous, holy rock. And scoria. Scoria. The gray version of it, the blackish gray version of it, is what we see in lab. And again, that's what they used to put in gas grills back in the day. Then they went to these ceramic briquette things, and like I said, nowadays they're just gone. So if you went home and opened up your parents' gas grill, you'll just see those boring old heat shields. But the first couple I tried to stay true, and you could still find this rock, so I pour that in there. But I gave up. So vesicular, it has vesicles, and we're not going to get into the details. Let me look. Yeah, we're not going to get into the details too much, but what I can tell you is that, as he and I were just talking a couple moments ago, this one and glassy are extrusive. They're lavas, okay? And what we usually see then with the vesicular, at any rate, is that this is a very gassy lava. It's got a lot of gas embedded in it. And when it comes to the surface, the pressure's lower, so all that gas bubbles out. Kind of like you open up a bottle of soda, and you pour it into your glass and you get that head that forms on top. All right? That head, that foam, is a structure formed when the CO2 bubbles come out, and I don't know if it takes the sugar or what aspect of the beverage it brings up there. Does the same thing with beer, so it's not necessarily a sugary sort of soda thing. At any rate, and it leaves that structure behind. Well, imagine if you could sort of slice that off and set it aside. That's what these vesicular rocks are. It's the foam that rises to the top of the lavas. All right. Glassy, on the other hand, is there's other stuff going on, but essentially we're just going to say that it cools really, really, really quick. It doesn't even allow crystals to grow. You may or may not know that glass, like windows here, okay, those are non-crystalline. And that's why if you look at, you go into very old houses or you go to some of these living museum kinds of places, the glass is actually thicker at the bottom than it is at the top. It flows, all right, largely because it doesn't have a crystalline structure inside of it. So, since we gave you pumice and scoria, we'll remind you that this then is obsidian, volcanic glass. All right, and when we do get to the rock test down the hall eventually, I need you to say obsidian, not volcanic glass. Okay, you've made it 18 years saying volcanic glass, maybe, but geology class now, you gotta say obsidian. So those are textures, and that is one of the two ways that we identify igneous rocks. It's sort of like a bingo chart, okay? You got a set of qualifications one way, horizontally, and you got a set of qualifications vertically, which is where we're heading in a moment. So you got texture, and then you got composition, which is right after this slide. So here's our textures. Not the best, but I tried. You've got your coarse grained, your fine grained. That's a much better example of fine grained up there in the top middle of what you'll see. The picture earlier was, like I said, kind of looked like you could see different colors. Coarse grained, fine grained, mixed grained, porphyritic. Then you're supposed to see little holes in here. This one kind of looks porphyritic as well, bottom left. And then I found a fancy square of obsidian there. Not all obsidian is just jet black, okay? Some of it has beautiful red swirling through it. maybe you're familiar with snowflake obsidian. Snowflake obsidian has bits of ash in it, and it looks like little snowflakes on it. It's cool stuff. So, those are your textures. Okay? Again, before we move on to composition, questions about texture. All right. As I just said, so igneous petrologists, those are people who not only go to 4 years of geology school, but 2 more for masters and then 2 more for doctorates and really, really, really like igneous rocks. There are some, like 6 people out there. No, there's plenty. They have 2 criteria: the texture, as we just said, and then the mineralogical composition, which is what we're going to talk about now. All right. You saw these words a couple times, and I said don't worry about them. Now it's time to worry about them. No, it's not hard. So felsic, mafic, and intermediate. On the tables and everything like that, you're always going to see felsic, intermediate, mafic, because intermediate means, of course, in the middle. But discussionally speaking, we want to talk about being felsic, and then we want to talk about being mafic, and then we say, oh, well, being intermediate is a mixture of those two, so that's why it's third in the list here. And what this is based on is the mineral content of the rock. Or, to go back and belabor a point we made earlier, the elemental composition of the magma or the lava, right? Because it's the elements that make the... In fact, you could even kind of say that it's predetermined what you're going to be able to get out of it. You'll have a felsic lava, you'll have a mafic lava, based on the percentages of ingredients. So this is what makes people nervous. And yeah, I can't say I would have made a better diagram, but this isn't great. So we got a lot of stuff going on here. For the time being, ignore those giant arrows in the middle-ish. All right? I also, because of our emphasis in lab on this, I also would have put this thing across the bottom that says silicic, felsic, intermediate, mafic. I would have put that at the top, because that's the names of these columns. And this is the stuff that you need to know. So why not start our diagram with the names of the things you need to know? I don't say silicic a lot. It sounds kind of dirty. I don't know. So I say felsic. They say silicic because they're silica rich. Okay. Now, that being said, what is the most commonly occurring mineral group in the Earth's crust?
Silicates.
Yeah, silicates. So every single one of these suckers are silicate rich, but these are even more so than the others. Okay. So at any rate, everything's got silica in it. And every single one of these minerals is in what group? Take a second to look at them there. All right, so fair enough, you don't recognize half of them. But yeah, they're all silicates. We're going to rename a couple of these, conversationally speaking, and definitely when we get to lab. When I put together this chapter in the lab book, I wanted to switch to the names that we use. And again, this is just those igneous people being obstinate. Every single book that I looked at, and I looked probably half a dozen different intro lab books, they all do this. They teach you albite in minerals chapter, and then when we get to igneous rocks, they change and refer to it by its elemental composition. So, anywho. Such as it is. We smile and nod at those people. So you got a couple names up top that you might recognize, maybe. Granite, for sure, right? Beneath that, rhyolite. Then we've got diorite and andesite and gabbro and basalt. Let's ignore peridotite for the time being. Mostly forever, but we will acknowledge it in a moment. So granite, rhyolite, diorite, andesite, gabbro, basalt. You're going to see those 6 rocks in lab after we're done with minerals. So I think that's starting Wednesday for you guys. Okay? You folks at home, you've got a week still for that. What we're saying is that granite and rhyolite are composed of some mixture of biotite, sodium-rich plagioclase, potassium feldspar, and quartz. The only difference between granite and rhyolite, then, if you look to the instructions on the side, is whether or not they're coarse-grained or fine-grained. So arguably, the only difference between a granite and a rhyolite is grain size. The only difference between a diorite and an andesite or a gabbro and a basalt is grain size. Now that being said, you're going to have a hunk of granite and you're going to have a hunk of rhyolite. Those 2 rocks could have come from 2 completely different places on the planet. They are not related, okay? Other than on this table that we made to try and explain Mother Nature, we're saying they have this composition, generally speaking. Because think about it, there's a reason they made these little triangle-looking things. Otherwise, they could have just put, nice straight bars like the dashed lines are, right? So what's the point of those wide, skinny? That's because as the composition of one increases, let me try and do this with the mouse. So let's say you go right here. All right. Let me start a different way. Any given hunk of granite or rhyolite could be represented by a straight line drawn up and down through anywhere in this block. It could be over here. It could be over here. What I was attempting to say a minute ago is, let's say that rock is a straight line right here. So from here to here measures its potassium feldspar percentages. And then that means it only gets, this tiny bit of sodium-rich feldspar. However, if the rock was over here, we got a whole bunch of sodium-rich feldspar, but only a little bit of potassium feldspar. We're going to attempt to explain that a little bit, all right? But this goes back to those formulas I told you didn't have to worry about. And you still don't. You just have to acknowledge their existence. Because let's use the correct words that you guys know. We got orthoclase, feldspar, and albite feldspar here, okay? Your pink one and your white one. You don't remember their formulas, but they have formulas. And since they're both feldspars, can we assume that a good chunk of that formula is exactly the same? Because they're both feldspars. So they've got to have something in common beyond the SiO. And they do. And there's just a little something that makes it turn orange versus making it turn white. Possibly the potassium versus the sodium, eh? So, at any rate, since you're pooling the same ingredients to make those minerals, well, arguably you have to make less of the other one. And I'm getting a little ahead of ourselves here, but I am trying to explain this table here. You'll see it again in a couple minutes if you're still not on board with me here. So a felsic rock, to summarize, can be represented by a single line through this felsic column. And the one in your hand might plot over here, and your neighbors in lab might plot over here, but they're still granite or they're still rhyolite. Similarly, a diorite can plot anywhere in here, a gabbro or a basalt can plot anywhere in here. Your job is sort of to eyeball this and say, that's what these percentages are over here for. Okay? I see 35% albite in this guy. So that means roughly it's going to be here. That means we have that much orthoclase. We have that much quartz. This must be a felsic. 9 times out of 10, you're going to recognize it as a granite anyhow, right? But that's the scientific method going on in the background. So you're going to have 6 rocks, all made arguably of the same stuff. The only way you tell the difference between the two is whether or not you can see the minerals or they all blend together into a new color. Okay? It's a lot simpler than I just made it sound, trust me. All right. So what else is misnamed on here? We got amphibole and pyroxene. Pyroxene, I always mix these up. Pretty sure pyroxene is augite. Amphibole is hornblende.
Yeah, I think so.
Okay? And I put those actually in parentheses in the lab book because I knew we'd see this. I don't know why I didn't put the feldspars and the plages in there. Again, I think you can take an entire class in feldspars. I don't know why, but you can. And the plagioclades are types of feldspars. It's wild. So amphibole, hornblende, pyroxene, augite, you know those names. Biotite, you know. Quartz, you know. I did tell you that it's kind of smoky quartz that we're going to see. It tends to be grayish. I don't know if there's a particular reason or not. Your albite and your orthoclase. So all the way over on the right then, you see that word ferromagnesiums. That just means iron and magnesium. And then you see olivine. You're like, ooh, I know olivine. I actually remember olivine. It was green. Olivine green, 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 green. And for some reason, they even made this green. I don't think it's related. And you got peridotite. Peridotite is this really funky, ultramafic, as it says down there at the very bottom. Really, really mafic. It's an igneous rock composed almost entirely of olivine. And if I had to guess, I'd say that our specimen for the test of olivine is probably a hunk of peridotite. Okay? It's one of those things where, where does it stop being a mineral and start being a rock kind of things, and there's no real answer. There's very few. We mentioned halite will become rock salt when we change to sedimentary rocks chapter, okay? Olivine becomes peridotite when we turn to the igneous rocks chapter. At any rate, we don't have in your lab books, we don't have the ultramafic category. Going back very briefly to obsidian, if there was such a category, it would be ultrafelsic. Okay? Glass is silica, right? Quartz is silica. So we've got silica all through here. We've got silicate-rich ones over here called felsics already. There's other stuff in there. But when you get to the obsidian, not only does it cool really, really quickly, but it is also a special chemistry that allows that to form. So, it's a neat rock. It's a neat rock. No doubt about that.
So does the quartz help kind of cut out the biotite? Like if there's a lot of quartz, biotite can't exist much?
Hold that question for like 3 slides. Oh, one last thing. Again, I told you to ignore those arrows a little earlier. These are just generalizations that, again, talk about sort of what she was asking and sort of to where we're headed in a slide or two. All right? These are general statements that say increasing silica content heads towards the felsic side, heads to the left. Increasing potassium and sodium also heads in that direction. And then your iron and your magnesium and your calcium increases as you go to the right. They're just trying to explain, again, sort of the idea behind the mineral content. But what we have to keep remembering is that until these rocks exist, it's not minerals, it's elements. So we're not really seeing quartz at this point because we're still, well, if this were a magma, okay, and in my mind we're still talking about magmas and lavas because that's the next slide. So again, they're not the minerals until the crystals form. So lava and magma, just a reminder, okay? These are terms we use for the molten mineral mixture composed of elements. Magma inside the earth, lava at the surface of the earth. I'm not sure why I felt the need to put a reminder in here, but good. Okay, we got our 3 flavors. All right. We got the felsics, we got the mafics, we got the intermediates. We don't eat rocks, but I have to imagine these differences in ingredients, differences in chemistries. For those that do eat rocks, they might actually, have a preference. They might have a taste difference, taste profile.
My boss once, we have a German TV show. If I can just throw this in.
Sure.
It's like Wetten das, so it's like I bet that.
Okay.
And there are like people coming and somebody's betting that they can't do what they say they can. And he said, because he's also a stone sculptor, he said he can taste different types of stone.
Okay. So they do have different tastes.
Yeah, apparently they do, but he really wants to do this, but his wife wouldn't allow it.
To go on the show and eat rocks?
Yeah.
Yeah, that, you don't necessarily want to be that guy.
Yeah,
but
he was like, oh, that would have skyrocketed my...
Well, in the business, especially if he went on like wearing a shirt for the company or something.
Yeah, he would wear the traditional clothes, but like...
Oh, okay.
Yeah, apparently he said like he could tell 20 different types of stone apart. And, like,
Wow, by taste.
Because you just get it in your mouth.
Well, yeah, you get the dust, I'm sure. Yeah. Wow, that's wild. Yeah, there is a point in time when we get to sedimentary rocks that's one of the things we'll talk about is you rub it on your teeth for grain size. Because silts and tell the difference between silts and clays. One of them is still gritty and the other isn't. And if you really, really cared whether or not what kind of mudstone you had, whether it was a siltstone or a clay stone, because that's the only way you can tell. You could arguably use your fingernails, but those aren't even smooth enough. So the teeth is it, and geologists eat rocks. Yeah. Sedimentary though, don't try to chew on igneous or metamorphic. That's bad for your teeth. All right, so this is essentially the same chart we just looked at, cleaned up a little bit. What is the letter K, elementally speaking, represent? Potassium. All right. So potassium feldspar is your orthoclase. The sodium rich is your albite. And something cool that we'll talk about, and I told you that the plagioclases, you can take an entire class on feldspars. This bar goes across all 3 of these columns because this is like a plagioclase spectrum here, okay? And you change from albite over to some dark thing that's kind of like labradorite, but doesn't have the cool flash or anything like that. We just call it dark feldspar. It's kind of like the force. We just, So over there, again, we don't have names for it, but it's all connected. And we're getting to that conversation here in a moment. I just wanted you to see this slightly cleaned up version. Again, it still has the ultramafic down at the end. But they've got the percent by volume cleaned up a little bit, and hopefully it's starting to make sense what I was saying about, any given rock is one line through here. And then you see these line segments. It's hard to do with just the mouse, but say that one, and then you go over here and you say, okay, that goes to about here. So we're looking at 25% quartz, which means that much here, which is, let's say then that it's 40% orthoclase. I used to have you guys do that in lab. Bang for the buck, it's not worth the time for our purposes anymore. I kind of thought it was important for a long while. And that's why I'm talking about it in lecture. And maybe it's easier if you had the rock in front of you. But we don't measure the percentages anymore. And then once you get past, please ignore granodiorite and dacite. Once you get into diorite and andesite, it's almost impossible. And then when you get into the gabbros and the basalts, it's totally impossible. You can't. Everything's black in the basalt, with the possible exception of a little bit of olivine. So, and even in the gabbro, I mean, where it's coarse grained, it's all black. So, it really only worked with the granite, kind of worked with the diorite. All right, next. Next. Not that you're going to be doing this, but you can't just melt all rocks at the same temperature. Can't throw them in the bonfire. In fact, you shouldn't throw rocks in the bonfire because certain rocks will explode, like if you throw sandstone in there, the water inside of it.
Don't give me that news.
It can pop, and you get a lot of shrapnel everywhere. It's not a good idea. But it can. So that's why you got to be careful. Build your firing out of, particular stones, so on and so forth. So granite melts at a lower temperature than basalt. All right. Don't worry about those numbers. You're never going to have to regurgitate them. We simply need it as a means to an end right now. Because the thing is we're trying to grow igneous rocks, right? Not melt them. But we need to have this conversation about melting and crystallization because I think arguably you guys melt a whole lot more things than you crystallize. Really, the only thing that you ever crystallize is ice, water, right? I mean, maybe you guys, maybe your household makes rock candy as a family tradition or something at Christmas, but there's not a whole lot of things we crystallize, but we melt a whole lot of stuff. And what I want you to realize here is that there's sort of two sides of the same coin. What temperature does water freeze at?
0 degrees Celsius.
All right, in English, somebody else. No. 0 degrees Celsius. How about the other one we know? 32 Fahrenheit. Good. What temperature does ice melt at?
0 degrees Celsius.
Not quite. It's a very thin blade, but there is another side to it. 4. Okay. That I don't know Celsius that well. But I was going to say, all right, 31.9, right? If it freezes at 32, it melts at 31.9. If it melts at 31.9, it freezes at 32. You could take those decimals out wherever you want. And in the Celsius world, again, I can't be of help. I apologize.
But if it freezes at 32, 31.9 is less.
Sorry, 32.1. Thank you. The Celsius threw me off.
Yeah, that makes more sense.
Yeah. So one, where is it at? And is there even smaller decimals? Yes, there is entirely. Okay. Yeah, 32.1. I apologize for that. So the same thing is true here. Okay. Because we're not melting rocks. We're trying to grow rocks. So what we have is this pool of magma or pool of lava that is at some super high temperature. Why? Because the whole thing is, it's lava, right? It's molten. It's super, super hot. But as it comes to the surface or as it moves farther away from the core of the earth, it's going to start to cool down. So if we're at a number arguably that is higher than 1,000 degrees Celsius, as we start to approach 1,000 degrees, if you have a mafic lava, you're going to start to crystallize some of the minerals that are in basalt. If you have a felsic lava, hitting 1,000 degrees isn't going to do a damn thing. All right? You got to keep going and going and going. And then when you get at a certain temperature, you'll start to grow some crystals. What we are talking about is something called Bowen's reaction series. And this goes back to when you asked the question, I said, please hold on for a couple slides. We're there now. And it wasn't that quartz steals the ingredients from the other guys. You'll see that quartz is because that's all that's left. So what this guy did was he basically spent some time watching lava cool. All right. He, might have made some simulated things, got a furnace going really, really hot. Can't always travel to active volcanoes, right? And what, we'll just say Professor Bowen figured out was that there is a predictable sequence that minerals will crystallize in a cooling magma or lava. If the proper ingredients are present, this will grow, then this will grow, then that will grow. And of course, there's a wonderful diagram to help us explain it all. So what this tells us is that not all minerals crystallize at the same temperature. We're going back to our opening slide, not all minerals melt at the same temperature. Same thing. Minerals with higher melting points crystallize before minerals with lower melting points. Because if it takes that much to melt you, that means you're going to grow sooner as you're cooling down. And this is, for some people, hard to swap around because, again, we're trying to grow crystals and we're used to melting stuff. So, all right, let's see that. No, we're still not going to see that diagram. Don't worry so much about this. I'll explain it when we get there. There, finally. Damn diagram. Okay. So, we got our mafic, our intermediate, and our silicic, our felsic over on the side this time. And it means the same thing that it did before. Anything to the left of that word mafic are minerals that you would have seen underneath it on the other table. Anything to the left of the word silicic is anything that you would have seen underneath felsic on the other table. Basically, if you take that bottom right-hand corner and flip it up to the upper left, boom, you've got the same table. I don't know why they had to rotate it, other than to make something new and unique to confuse you guys with. All right. You put silicic in the upper left-hand corner instead of the bottom right. You flip that entire diagram. It's the same thing. All right. Anyhow. So, temperature arrow on the left-hand side. We're just going to make up a number. I don't know what temperature olivine melts or crystallizes at. You don't need to know what temperature olivine melts or crystallizes at, but we can acknowledge that it has a number, right? Okay. Let's call that 9,000 degrees. So we're going to start with our magma is at 10,000 degrees. Everything is molten. It's all elements, no minerals, no crystals, no nothing. It sits there. As it cools down to 9,000 degrees, olivine starts to grow. What's in olivine? Yeah, I don't know either. But we know there's stuff in it, right? Okay, silicon, oxygen, probably some iron, da-da-da-da-da-da. So, as it's growing that olivine, it's plucking that stuff out of the magma. You're baking cookies. You got your cupboard full of ingredients. You're pulling stuff out. You're using it. You're locking it up. You've made pretty green crystals. Comes down to 8,000 degrees. You stop making olivine. This is why that's called the discontinuous branch. You stop one, you start another. Okay? You stop making olivine and you start making augite or pyroxene. Again, what's in augite or pyroxene? We don't know, but there's stuff. So now you're plucking those ingredients out. More silicon, more oxygen, probably more iron. Because again, we're on the iron-rich side. Mafics are iron-rich. You get down to, what are we at? 9, 8. We're down to 7,000 degrees. Now we start making hornblende. You follow? The whole time you're using up ingredients. Now, to get back sort of to your question earlier, let's go down to biotite now. Let's say there's something in biotite that you used up making the hornblende or the augite. Then you're not making biotite. It kind of just sits there. All right. Muscovite is not really represented in here. Oh, there it is. Let's see, I'm not seeing it. Muscovite is in there, but it's at a cooler temperature. What will happen is you'll probably grow a lot more muscovite than you would have, because again, the micas are related, same last name, a lot of stuff in common. But because you didn't have some certain ingredient to make biotite, it doesn't do anything for that 1,000 degrees of weight there. Then when you get down to, let's see, 9876, we're now at 5,000 degrees, muscovite, you're going to grow some muscovite. At the same time, you're growing potassium feldspar. That is your orthoclase. What's an orthoclase? Same joke, okay? Stuff. You're plucking that all out. The assumption is then, by this point, you've used almost everything except your most basic ingredient, your flour and your sugar of that cookie cupboard, okay, your silicon and your oxygen. You got nothing but quartz. Now, if you've got a whole lot of silicon and oxygen left, you're going to make a whole lot of quartz. If not, then you get what you get. What this is explaining is why, again, in lab, there's going to be 4 boxes of rocks out, right? You're going to have 4 different granites. Your granite is going to look a little different than your neighbor's granite, and it's going to be a little different than their neighbor's granite. And you go to the countertop store. By the way, many of those aren't actually granite. But nobody wants to buy a basaltic or a dioritic countertop. They don't know what the hell that is. So they just call them all granite. I had this conversation with the poor kid working on the floor one day. He's had no idea what I was talking about. I'm like, where's the orthoclase? What? I said, well, you're calling this granite. There has to be orthoclase in it. I wanted to show him my diagram from the lab book. He's like, it's granite countertop, sir. Okay, that's fine.
Marble.
Yeah.
Yeah, like limestone. No, it's limestone. It's marble.
Yeah, marble is amazing. And I've had people ask me, much like you guys, asking me questions here. Why does this marble look so different than that one? I'm like, impurities. I don't know. There's just, little things, and marble's beautiful, beautiful. But you guys actually carve limestone then, too? Or you just call limestone? Because limestone's going to melt away a lot quicker than marble.
Yeah, but we're not melting things when you build them.
No, I just, yeah, but I'm saying, so somebody's cheaping out and getting limestone. Is it cheaper to build out of limestone?
Well, sometimes it's more of the area. So
Okay.
my apprenticeship was in an area where there was a lot of limestone.
Mhm.
So in Hofen, where the lithographs plates come from.
Okay.
So yeah.
Okay.
We use limestone.
Yeah, well, a lot of our tombstones around here, I don't know in other parts of the world or not, but are limestone. We're limestone. And it's the old ones. For one thing, it's easy to carve, but they're all worn away after, 100 years or so. You can barely read some of them. Then they moved to the granite and even the marble. Marble's still affected by acid rain, but again, it erodes a lot slower. Weathers a lot slower than the limestone does. But countertops, tombstones, statues, yeah. It's all right. So back to igneous rocks, right? This is explaining the variation that you're gonna see. All right. Same thing happens whether you're an intermediate or whether you're a mafic. Now, we had the discontinuous. You stop one, you start another one. It's temperature based. The continuous is still temperature based, but it blends. All right. This really is a lot easier to talk about in lab when the rocks are in front of you. So I'm just going to kind of gloss over a little bit here. But, we're going to talk about the white stuff and the black stuff. There's sort of gray stuff in the middle. It's hard to see it. All right. But it is blending from the albite, which is the sodium rich, that kind of dips its nose into the felsic column there. And then it says about equal calcium and sodium, then it goes up to calcium rich, all right? By the time you get to mafic, it's all dark feldspar. So when you're looking at diorite, which doesn't mean a whole lot to you right now, but it's diorite Dalmatian. It's the black and white one, okay? when you're looking at diorite, you're going to see white stuff and black stuff and clear stuff. The clear is quartz. There should be a gray in there, but we don't see it really. So, anywho. So what this guy is explaining is that essentially, from the get-go, there are 3 different types of magma pools. Mother Nature doesn't plan it that way. It's just what's dissolved in it, right? It's only us coming along, measuring it and saying, oh, this has this percentage of that, this percentage of that, this percentage of the other thing, so it must be this. She doesn't care. Doesn't need names. As I always like to joke, nature doesn't need math, okay? I like telling that to the physics people. Math, calculus is just us trying to explain physics, right? So it happens, we observe it, we write it down. Same thing here. These pools will grow what they're going to grow because of their ingredients. All right. So what do you need to take out of all this? What you need to take out of all this is just a couple things. Basically what we said on the previous slide. Not all minerals crystallize at the same temperature. Okay? That's that discontinuous branch there. Also, they all need different ingredients. You knew that. And lastly, once you use up an ingredient, you can't make any mineral that needs that. There's no running out to the Quickie Mart to get more chocolate chips. Okay, whatever. Baking powder. You got what you got, and you can make whatever you can make. So these are closed systems, to use the real word. So. Questions about Bowen's reaction series? Good.
Could you kind of repeat those 3 things again?
As I always say, not exactly the same way, I'm sure, but I have 3 summary points. Yeah. So different minerals crystallize at different temperatures. Different minerals need different ingredients to form. And then once you use up an ingredient, an element, you can't make any mineral that needs that element. And that explains the absence of some minerals and also the prevalence of other minerals that are related. We didn't get into it too much, but like I said in one of the earlier examples, if you don't make any orthoclase, you could make a hell of a lot of albite, okay? Because you have the leftover ingredients. Now, how they know to form, to one another and all that, that's chemistry. And is totally beyond my realm. Why this bonds to that to make the other ingredient, okay? But I'm sure there's equations and pluses and minuses and valences and whatnots to explain it all. All right, good questions. What else? Okay. Because we got to do just a little bit about intrusive igneous rocks to make this official. Let me look real quick, see if I name. Yeah, I don't name. One thing I am going to add new. All right. Imagine there's a new slide here. Just a reminder, throwing around some of the names we've been throwing around. Your igneous rocks. Actually, let me just make the slide because this is, at least today, I feel this is important. If I can remember. Start up here. Can't remember the name of the one that's under granite. Rhyolite andesite basalt. Thank you. All right, so just to give it in some context, thank you for your patience there. Just to put it in some context, the rocks we were talking about, okay? We have 3 examples of intrusive igneous rocks that you'll become familiar with. The rhyolite. I'm just totally stupid today. Granite. Diorite. And gabbro. Those are your, because they're coarse-grained. We want our intrusive rocks to be coarse-grained. Those are 3 examples of rocks, igneous rocks, that you guys will become familiar with. I'm trying to get this out of the color now. It's all the fine-tuning we do. Make our PowerPoints look pretty. Okay, take 3. So, gabbro, diorite, and gabbro are 3 of the rocks that you'll become familiar with. One of these is felsic, one of these is intermediate, one of these is mafic, okay? So, how does this ever even happen? There's a point where it's molten, of course, and we need to move away from there. I'm Sesame Streeting this up a good bit here, but essentially what happens is we're bringing these guys up into the crust. All right? The Earth is old. She's cracked. And magma works its way up through those nooks and crannies and gets to a place where it is cooler. How do we know it's cooler there? Well, for one thing, the crust is solid, not molten. So it is cooler. Okay? And it intrudes. Intrusive. Now, slowly begins to crystallize. Like I said, we don't really put numbers on this. Obviously, some can cool faster than others. We have those different chemistries. Remember, we told you mafics were reacted a lot hotter than the felsics did. A whole lot of things. But let's again just say this is on a time frame of thousands of years. Okay, very generic answer. Now, what this is really an excuse for a conversation about is igneous intrusions. Dikes, sills, and plutons. I do have a diagram coming up in a moment. Pluton, I said offhandedly an hour ago, was a pool of magma or lava underneath the surface of the Earth. When we draw one of those generic volcanoes that you might have drawn when you were in 3rd grade, the pointy little mountain with the hole in the top, and we got to draw a pipe down the center, what do we always do? We put a pool of magma down at the bottom, pool of lava down at the bottom. That's going to feed that, right? That's the Pluton. So, arguably speaking, what we're talking about here is that that's the magma or lava leaked up from the mantle, crept into the crust, filled up a giant area, which is our Pluton, and then it leaks out from there. Okay? Basically, a pipe works. And all we're using are 2 different words to describe which way those pipes are oriented, which way those pipes are being laid. Either horizontal or vertical. That's contextual, but it's good enough for our purposes. Because what it really truly is, as you'll see in a moment when we get to definitions, is it's relative to the way the rocks are laying. But, for our intents and purposes, vertical and horizontal works. Because I always draw nice, simple diagrams for you guys. We're covered by sedimentary rocks at the surface, right? Most of you know that. Sedimentary rocks tend to be flatly layered, horizontal. So, sills are anything that is with those horizontal layers. That's the horizontal. The dikes are anything that's cutting through those horizontal layers. And again, you'll see a diagram in a moment. And you'll see some wonderful new vocabulary where it's concordant and discordant, of which we know one of those words probably. So, relatively speaking, a nice cheater is dikes are vertical, sills are horizontal. Because of my nice diagrams. In the real world, it could be slightly different. What is Discord, other than that chat server thingy?
Disarray?
Disarray, good. Anybody from the musical background here?
Is it the part for this?
It is not the chord for dis. No. It's when stuff clashes, right?
Yep, that's what
Somebody's really off tune and they've created discord. You don't say it that way, but that's you know that's a word. So yeah, discord is this is against. Okay. Concordant. Con means with, apparently. I don't know how that works with config, but maybe it doesn't.
So concordant is like a group, like an agreeing group.
There you go. Yeah, they're cordant.
Interesting.
So again, prefixes and suffixes don't always work out the same way, but sometimes. And like I said, that the con I'm not sure about there, because in this case it's a good thing. It's going with the grain. And that's another thing. If you're from the carpentry world, you could think of this as with the grain and against the grain. Okay. Discordant is against the grain, because all of this is relative to the rocks you're in. I'm setting it up so you're in horizontal layered rocks. Let's get that picture up. All right, horizontal layered rocks, which is mostly what we see at the surface. Every so often, if there is a crunching event, things get roller coastery. We've all seen those rocks that take the big dips and dives driving along the road. But for the most part, things are more or less flat. So, when this lava or magma squeaks up to the surface and it follows a vertical path, we label those as dikes. When they take time to spread out and follow maybe a crack that's in between the beds, the layers, all right, because there's always a weak spot when you switch from one rock type to another, then we call those sills. I think a sill, like a windowsill, is also another way to think about it. They're flat, horizontal. And a dike is kind of like a dam. And those are sort of vertical. They're holding back water in that way. We got our Pluton down at the bottom, the big pool of magma that's feeding all this stuff. Don't worry about laccolith. Oh, so your book is going to mention laccolith, batholith, Plutons. They're going to tell you about sizes and diameters. We don't give a rat's behind about that in here. Okay? Don't worry about that. You got enough vocabulary where it's going.
They're pretty much lava tubes, correct?
Kind of lava tube. Lava tube is yes and no. Lava tube is a very specific thing at the surface of the earth. So we don't want to use that word right now. But if in your mind, that's why I use pipeworks. Okay? We're so far removed from it, but there used to be a screensaver in Windows that would just build pipes. Okay? I don't know how far along it made it, probably not past Windows 95. But enough people still kind of know that. And that's what we're doing, is just building those pipes there. It's following these existing cracks, expanding them. There is some pressure involved here. And it goes towards the path of least resistance, right? Like everything in nature does. At any rate, it's in these dikes and sills where more often than not we're finding these igneous rocks, where they're mining your countertop from. Yeah, somebody might find an exposed Pluton. Okay, especially when you get into mountainous regions like this, where the surface is all cracked up, and over the thousands and thousands and thousands and thousands and thousands of years that it's been sitting there, it wears away and sometimes leaves the harder stuff underneath sticking out. Canadian Shield, you may have heard of that. All right, but more often than not, we're hitting up these little feeders, these little things that come off of it. So after the conversation we've been having for the last half hour, this is pretty You guys keep waiting for the ball to drop. Okay, what's hard and confusing about this? That's it. There isn't anything else. It's just some nomenclature we need. See it in the real world. It's kind of hard to picture it as a pipe still, but that has depth, right? And arguably where they've cut it off is, now what would be interesting to see would be the other side of the road, to see if the dike is still on that side as well. Then you got a really big tube. Person for scale, kind of hiding in the shadows there. Whereas a sill, hey, my mouse is actually right there. All right. Whereas a sill is going with. And you see the rock layers, the bedding in there? If for some strange reason that that sedimentary rock had been turned sideways in some sort of tectonic event, mountain building event, and that lava was still cutting across it this ways, technically speaking, that would be a dike. Because again, it is relative to the rock that it's in. So, again, here the rocks are going horizontal, so this is cutting through it vertically, therefore it's a dike. Here the rocks are going horizontally, this is cutting through it horizontally, therefore technically it's a sill. We good? Yeah, it's all relative. Everything's relative. All right, so as that other slide alluded to, every so often there is just enough pressure and or magma underneath to push that sucker all the way through to the surface. And the earth gets another zit or a pimple. All right, and it breaks the surface and grows a volcano, which is another check. And we will mention more rock names, unfortunately for you guys. Same names, but you'll hear them again. We're going to hear the rock names more in the volcano chapter as well. So don't freak out yet that you don't, have these down yet. But hopefully, once we do them in lab, again, you guys will be able to picture when I say, oh, basalt, you'll be picturing that fine-grained black rock that you had in your hand. When I say granite, you'll be picturing that coarse-grained pink, white, and black, rock that you had in your hand and so on and so forth. You'll get there. No worries.
Can you go back to the 31 or like 32 it is now?
Eh?
Yeah, I am there. Like we learned that there plutons, they could also be in the middle. Is that not a pluton?
So like this guy up here? So that's what I said. There's your book's going to talk about batholiths, laccoliths, plutons. There are different categories of those pools, and I don't talk about them.
But it's like different where they are.
My understanding is it's mostly size or diameter. I'm not sure about the location. It might be that one is a supplemental is not the best word for it, but a secondary pool. Yeah, that could be implied in those. Again, it's not something I ever paid too much attention to, and certainly nothing that I've ever taught in here. When you're reading that chapter in your book, if you come across that, let me know, and then we'll both know.
And also, the pipes that go up, are they always called volcanic cone?
No, that is the cone. Is the volcano? It's just another name for the volcano. When we get to the volcano chapter, we're going to explain that they call them cones. We call them mountains. The vent pipe, please don't pay attention to anything above the surface on this diagram.
Okay. But like everything that goes up, is it dike then?
As long as this is what I was talking about with it being relative. So as long as your beds that it's cutting through are horizontal, anything vertical is a dike, yes. All right, it's a relative thing. That's what I mean. If it's It's a perpendicular versus parallel kind of thing, is another way to talk about it. So in this diagram, where we have horizontal beds that you're cutting through, vertical does equal dike, and horizontal equals sill. On the test, should I give you a diagram, I would keep it exactly like this. You would have your horizontal bedrock that you're cutting through, okay, and therefore vertical is dike. But as I said in one of the pictures I showed you, if for some strange reason these layers here were actually going up and down, okay, then the fact that this is cutting through horizontally would technically convert that to a dike by definition if this rock was going this way. But it's not. So it is, that's what I mean by it is all relative. And I rig the game in your guys' favor. Okay, I draw pictures that fit that rule. But out in the real world, you got to look at what the background rock is doing. Does that make any more sense? Okay. What else? Okay.
So the rock practical is next week?